So this is probably the most nerdy, most technical presentation I could give. So we're going to talk about vector operators in Solr. This is a thing that we've had for a couple years now, and so I just wanted to kind of to show how we've done sort of a Tanimoto and Cosine Similarity vector operator, and there's a lot of source code. So for those of you who like source code, I should probably, looks like the trend is for more people on this side, so I might point to some things. So just a couple slides that my marketing department demanded I stick in here. So this is, we are Accenture. We're an extremely large consulting services organization with about 460,000 people, which is astonishing. If we were a country, we'd be number 15 or something. I don't know. No, not 15, 38. Within Accenture, we're inside of a smaller group called Applied Intelligence, which is a lot of data scientists, PhD data scientists, and that's our group. And then within Applied Intelligence, our group is Search and Content Analytics. We are an acquisition of about 2 years ago of a boutique consulting firm called Search Technologies. So if you remember Search Technologies, we are now the Search and Content Analytics group of Accenture. Okay, so why create a vector operator? I can think of 4 reasons. You have vectors to search, right? So that's the most obvious reason. The only good score is a percentage score. So, I am honestly sick and tired of scores which are anywhere from 0.05 to 32, right? And it's like, what does that number mean? It has no meaning whatsoever. Wouldn't it be nice to have a true similarity score from 0 to 1 with some actual mathematics behind it? Wouldn't that be a relief? That would be such a relief. And we're going to show it. Your documents have intimate relations with neural network embedding vectors. So, neural networks starting to become a really big deal. So if you're doing BERT, for example, or if you're doing, what was the other? Oh, the universal sentence encoder, you're probably generating vectors. You could reduce the dimensions on those vectors, perhaps cut off elements that are too small and then store the results and do vector similarity comparison based on neural network comparisons. Super useful, super cool. You want to pre-compute all your term weights because you don't trust anyone else to do it right. That's me, right? I just don't trust the magic that's in the machine. I really want to know all the mathematics that are involved so we can actually store the weights in the index, and those weights are the ones that are actually used, not some computed on the fly TF-IDF, and you're like, well, I have no idea where these numbers came from, and so on and so forth. Well, I mean, of course I do. I have the source code to the similarity class, but still, it would be nice to pre-compute them. And the other thing is you can use, as much machine learning and Spark mathematics to compute those term weights as you want, creating algorithms that are super complex, which would not be able to be done on the fly. And so here's a sample vector. So this is a vector which we'll be using for our demonstrations today. It's from SOC-ONET. So we created vectors for all of the job codes in the occupation codes, which is ONET. And so we see here, it's a list of terms like income tax advisor. Some of them are multi-word terms. Some of them are single-word terms. And a weight, 0.226. All the weights are between 0 and 1. The entire vector, in this case, was normalized to be of magnitude 1.0. And so we have tax specialist, 0.204. And you can take a look at this and you can say, yeah, I kind of understand what type of job that is based on the vector of these terms that are in the job. And so you could take this vector, for example, and try and find, match this job title to resumes and start tagging people to SOC-ONET codes. And that's the exact sort of thing that we do with this vector operator. Okay, so let's dive into the details of doing this. And I have 40 minutes, so I just need to be super careful because this could quickly spin into a lot of detail. So the first thing we need to do is somehow index the vector. And so we're going to create a custom analyzer to index the vector. The vector in this example is, hello world love, because there's not enough love in the world. So I use that as my example. And so each one of these words has a weight. And so the question is, the analyzer can take this text from the vector field and split out the tokens, which can be multi-word tokens or single-word tokens. And it has a weight for all of these. So the biggest question is, where do we store the weight values? And there's really two options. One is you can actually store it in the position data. That's a little flaky, but it totally works. And the other option is we can use payload data. So because, I've never quite, because the payload data is sort of an extra access, I like to use the position data because things are a little more optimized for the position data. But the tricky part is it must be in order from lowest to highest. So you actually have to reorder the terms so that you index the lowest strength term first, because the positions will start off at 0 and go up. Okay, so this is step one. We're indexing the vectors with our analyzer. And so this is the code sample for the analyzer itself. And there's, it's actually about 1/5 of the actual code. I just tried to pick out the parts that were most important. This would totally not work if you tried to do it. But the important parts is the tokenizer, which is part of your analyzer, actually has a reader, and a Java reader to read the characters. And that's this reader, this.input.read. So this.input is the input to the tokenizer, which is a stream of characters, right? So then you read a character, and then you just load that up into a big vector string. In this case, I did it as a big vector string, which loaded into memory because I have to process it in reverse order, right? In this case, all of the terms were from strongest to weakest, but I need to actually store them in the index from weakest to strongest. So I actually just load the vector and traverse through it in reverse order. Every term, you append the characters to this thing called a term attribute. You set the length, and then that term attribute is actually communicated up the analysis stream to the next analyzer. Then you extract the weight from the vector. In this case, I just need to convert the weights to an integer, which is the position data. So I just multiply it by 1,000 to give me 4 digits of precision. I round it off and store that in the position. And then I just have to keep the positions because the positions are incremental. So I just take what the new position is minus the current position, set that as a position increment, and that's how the weight gets stored in the index. And along the way, I compute the magnitude of the vector, so I can also index that later. Okay, so far so good. And we have a demo. So here's my vector to analyze. Localhost 8983. Go to my SOC.NET core, go to analysis, enter in my vector text, enter in the vector field and analyze that. And look, we got nothing. But if we start scrolling to the right, if we take a look at the weakest one, right, because that's going to be the first one that we see, here we have financial information. So that's our token. It's at position 49. So if we look at the value here, we see that it's rounded up 49 to 3 digits. So I guess I'm only loading in 3 digits of to the right. So then the next one is going to be data entry. So that's data entry with a value of 79, which is rounded up to 80. Deductions, which is a value of 87. Detect errors, and so you can see where the token here is ending up as the position data in the index. Now, if we scroll all the way to the right, we see a special token called the magnitude token, which has the magnitude of the total vector, which in this case is 1.0. Easy peasy. Make sense? So there you are. Now, I didn't trust the search engine to create the weight for me, right? So I pre-computed the weight. stuck it in a field, and stored it in the index, because I don't trust things that I didn't write myself. You know, except for Lucene. Okay, so moving on. Okay, so the second step is we're going to create a term operator which just fetches that weight that we had pre-computed for that index from the index. Okay? So I don't know if has anybody created their own operators before? Raise your hand. I know some folks over there have done it. Okay. So, you know, part of this is to sort of encourage people to dive into creating their own operators. Turns out it's a little mind-bending to start with, but once you get used to it, it's not that hard, and you can steal some code from Lucene and make it easier. And, you know, this is, sorry, I'm sure the Accenture lawyers would have objected to my use of the word stealing. Leverage. I mean, it is Apache too, so I'm probably safe. So what part of this is just to start encouraging people that if you don't like the mathematics that you're getting, to create your own, right? Because it's really not that hard once you get used to it, and we should all be a little less afraid of writing our own operators. And so, you know, I'm hoping that when I come here next year and I ask that question, how many people have written their own operators, you know, I'll get at least 3 times as many people have raised their hands. So that's part of why I'm doing this presentation. So there's actually 3 sort of classes you need to create when you create your own operator. And each of those classes has a different scope. And that's why there are 3 classes. The first class is a query class, which inherits from Lucene query. And it really represents the query that's independent of the index that you're searching over. And so you can take that query object and apply it to any index, although, you know, of course, it has the field name associated with it, but it's not really tied to any index statistics in any way. And so you know, this gets created with no reference to the index, typically. The next class is a vector term weight, and its scope is sort of the index as a whole. And so it takes index statistics. And this is where things like IDF are computed. All of the data that you would need to compute, which are independent of the specific document you're looking at, right? So now IDF is the inverse database frequency. So it's the database frequency across all the documents. So it's not a statistic that's specific to any one document, right? It's an aggregation of the data across the whole index. And so that's computed at the vector term weight as part of the index statistics, and then that's what the purpose, that's the scope of the vector term weight. So we're tied to an index, but not to any particular document. Make sense? And so then finally we have the scorer, and the purpose of the scorer is to construct a score for every individual document. And so a stream of documents come out of the scorer. And you know, this is where the actual sort of the magic happens, where it produces the final score for that operator for that particular document. Now, in our case, what we want to do in our score, right, is we want to fetch that position information for that term for that document, and then just report that up as our score. You know, divide that by 1,000, and that's the score. So that's what our vector term score is going to do. It's going to actually get the first position of the first occurrence, the only position, the only occurrence of that term in that document, figure out what its position data is, and then just, you know, upload that as the score for that term for that document. Okay, so I'm going to go through each of these classes briefly, and this is why, you know, I need to be very careful about time because this could take forever. But you know, just to point out a few things, vector term query extends query. Vector term query, I'm going to take as an input a span query. So the span query is what returns the position data. And so that's going to be actually an input to the vector term query because you know, I don't want to have to bother, you know, actually fetching the position data myself. I might as well, there's already an operator to do that. So I might as well just pass that in. And so then this vector term query has a method called create weight. And so the query creates the weight, and then the weight creates the score, and the documents come out of the score. And so here's my query. It creates a weight. The output is a vector term weight. Here's my vector term weight. It has a function called score, so it creates a new vector term score and returns that. And so basically, the span query is just the sort of the inner nested query, which fetches the position data. And so I'm going to create an inner weight for that span query, and then I'm going to create an inner score for that span score. And so my term query, term weight are really wrappers around the scorer. And then the last part is, this is this vector term score itself. And the part that's important really is this score, where you actually fetch the score of the document. So we just get the spans, we get the starting position, and then we divide that by 1,000 and multiply it by the output boost. And then that's the result. So pretty straightforward. So let's do a demo. So I have in Eclipse just Lucene all by itself, because all we're doing is Lucene at this point. There's no Solr involved. So I'm going to just enter income tax advisor, and this is my output boost of 1.0. Right? And so in this case, income tax advisor, we see this was a vector that was stored. The weight that was stored was 0.2266, which was rounded up to 0.227, and that's the actual score for that query that came out. So the number I put in is exactly the number that came out. It is such a level of transparency that is such a relief when you see it happen, right? Because you don't have to figure out how large the document is, what the average document size is, what the term frequency is, what the inverse database frequency is, and somehow multiply all those together to figure out if it's giving you the right number, right? The number that went in is just the number that came out. So, you know, I don't know how much you've spent on explain, Lucene explain, trying to explain to your customers why this document is above this other document, but you end up doing a lot of, a lot of hand waving. But in this case, there's really nothing to explain, because here I have local area network. Its value is 0.432, and out came 0.432. Cool, huh? So clean. All right, moving on. So the next step is to create the, excuse me, I have water here. I shall use it. Is the vector operator itself. So what we're going to do is we're going to create a vector term operator for each of the individual terms in the vector, right? And we're going to give each one of those a boost. And those will be the query weights. And so what's going to happen, is for every document, first we compute the query magnitude, right? Because in order to get a true similarity score, we're going to need the magnitude of the query weights and the magnitude of the document. Now, this is something, if you look at like Lucene, and you go to the relevancy scoring, and they say, well, it's a cosine similarity score. But it's a cosine similarity score without any vector magnitude normalization. They basically just multiply things together and add them together, and that's your output. But we want a true 0 to 1 similarity score, so we can't take shortcuts like that. We want a number that is really from 0 to 1, so we really need to compute the query magnitude and the document magnitude. Okay? And so in this case, the query magnitude, we're just going to take these weights, right, square them and square root them, and then we get the magnitude value of 1.146. So now we apply those vector terms to the individual documents, and we get the weights of each of the term Custis, the term Martha, the term George, because we're in Washington, D.C. Martha Custis is, anybody know? George Washington's wife, that's her maiden name. All right, so little history lesson. Okay, so we get the document weights, right? These were pre-computed and stored in the vector field. So we know that Custis was stored for a document at 0.9, Martha was stored at 0.65, George was stored at 0.1, and those are the weights that came from the position values, right? So we see the Tanimoto formula on the left. We want the dot product. So what we're going to do is just multiply the query weights times the weights that came from the document, add them together, and that gives us the dot product of the query vector and the document vector. But now we need to normalize that. So we're going to fetch the document magnitude from the document. We've already computed the query magnitude, so now we can compute the final Tanimoto similarity score, and that'll give us a number of 0.647. And so I just wanted to say, I've been using the word Tanimoto similarity, which is really like a bastardization of the Jacquard similarity index. And people complain it's not a true similarity score. But let me just assure you that as long as all the weights are greater than 0, it is a true similarity score. So just laying that to rest. Question?
So the 0.90 for custom is a position or is a pre-computed score?
It was a pre-computed score which was stored as the position data for Custis in the document. So I'm hacking the position score to store the pre-computed weight.
On what basis? Do you have a business rule if Custis comes, apply this weight?
So how do you come up with that score to begin with? Yeah, that's a subject for another day. But I could argue that that could be like from a neural network, for how well that term relates to the term around it, the terms around it, for example. And it could be based on a normalized version of TF, if you wanted to you could take the TF score and apply it to a sigmoid. What we've done for our customers, where this was super important, is we would go through all the terms in the doc. We'd actually get 1,000 documents, have an expert actually pick out the key scores, and then we do a logistic regression to compute this number, which is the keyness, or how important that term is to the document as a whole. And it would be based on the first occurrence, the frequency, whether it's a noun or a verb or an adjective or a preposition, how frequent it is in Wikipedia, is it in the title, a wide variety of different statistics that all go into this massive logistic regression, which gives us that number. So a lot of ways. And so this is, I suppose people sort of understand this already, but just to emphasize, Lucene actually pulls the documents from the score. So if this is a parse tree and you have an or and an and some terms, Lucene will actually call next on the top operator, which then is going to pull a document from the lower operator, which will then pull a document from the term, which will actually pull a document from the index, right? And then it sort of goes back and forth until it finds a document that satisfies the and condition, and then it goes and pulls a document from the other side. So it's a pull structure which pulls documents saying next, 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 next on the top operator, and the top operator then sort of proxies that down to the sub operators. Okay, so we're getting close. I have 20. I have until 3, right? I have until 3. So I've got 15 minutes. We can totally do this because we only have. There's 4 steps. So we're on step 3 or 4. So this is the vector query. Here's where we compute the magnitude of the input query. Here's where we create a weight for the vector query operator as a whole. What we notice is that we actually get in an array of the term clauses as operands to this vector query, right? And so we're actually computing the boosts across all those, and that gives us the vector magnitude for the query. And when we create the weight, we're actually going to get an array of the query clauses. Okay, and so then the query clauses that come in will fetch weights for each of those, and then that will construct the weight for this higher vector operator as well. So all these things are sort of propagated down the parse tree, right? Somebody asks the vector query, I need a weight, right? And the vector query says, oh, I need to compute a weight, so I'm going to ask for weights from all of my terms and then bundle them together into a new weight, a new vector weight class, object for this vector query as a whole. And then the scorer, so this is the vector weight class, which then does the exact same thing for the scorers. And so we get, we actually go through all the weight clauses, compute scores for all of those, and then we create a new vector scorer which has all the scores, and then also the magnitude score. So we have a score for all of the terms that are in my vector operator. And then finally, the vector score. Fortunately, we have this very helpful class in Lucene called the disjunction scorer. And so we can actually just create a subclass of disjunction scorer, and that does like all the work for us. There's a lot of, not a lot. There's a little bit of bookkeeping that I've like with two-phase iterators and things like that I'm not showing. But pretty much you can just extend junction score and just fill in your logic, and it's super easy. And so this is where we do the score. We go and fetch the score from each of the terms. That gives us the dot product. Because there's a boost already on that score operator, it already comes out multiplied by the query vector entry. That gives us the dot product. And then we extract the magnitude, and then we can just see this is the exact Tanimoto formula. Dot product over vector query magnitude squared, which I could have done ahead of time, now that I think about it. And ditto for the document vector magnitude scored minus the dot product. But that's the exact formula. And the cosine similarity, is even easier, right? It's just the dot product divided by the vector magnitude times the document magnitude. All right, and so, it's just right there. We tend to like the Tanimoto similarity better than the cosine similarity because cosine similarity wants the weights to be roughly equivalent. And Tanimoto similarity is a little less sensitive to that. And the Tanimoto similarity also gives you kind of more of a benefit for just having the term at all. Whereas in the cosine similarity, you have to have the term, and it has to be also of an equivalently strong weight. So we tend to prefer the Tanimoto as a similarity for text processing over cosine. All right, so we have a demo. I can just go back to my text here, extract the whole vector, and pass it to my vector operator. And here's the scores. So we see the search engine is searching over these pre-index vectors. When I entered just one, all it did was the single vector term query. When I enter a whole list of them, it does a vector query. And we see, with a little bit of round-off error, sorry, the first one is 1.0, right? Because it's the exact same vector that we stored as the one that we used for the query. So that's like, whenever you're doing vector comparisons, that's your very first smoke test. If I enter the same vector and I search over the same vector, the similarity score ought to be 1.0. And then we get nice percentage scores, which give us an idea of how close those two vectors are to each other. And they look good, right? Because here we have an income tax advisor. The second one is a tax expert. The third one is a revenue officer. Then we have auditors, accounting, credit and debt management. Then things start to diverge a little bit, like data entry, personal finance officer, loan officer, and then finally we're off the edge, which is, paste up artist or whatever. But these are good. This first set are really good, in fact. And this is, what we like to do, especially for recruiting and, industries like that. Okay, so the last thing we need to do is we need to stick this into Solr. And we're going to do this with an XML query operator. And I don't know. I would just say that we should get rid of all other query languages and just use this for Solr. Everything else is so arcane and hard to parse and impossible to read. Just forget all the others and just use this. Okay? So that's just my personal preference, but all of these, exclamation points and curly braces and hats and all that other garbage that you have to stick into and colons and whatever, just use the XML query operator. Okay, so this is what we're going to do, and this is what our XML query operator is going to look like, and it's super easy to read, right? Vector query, a bunch of terms. All the terms have a weight. So this is the query vector, right? And then those are the terms. And so this is what it looks like inside of Solr. We're going to create a vector query builder, which extends the Solr query builder, right? And this is about all that you need to do is create your vector query builder, extending Solr query builder. And what will happen is when it needs to parse your thing, it calls get query and passes in the XML element, which is a standard W3C element structure. And then it's your job to go through and fetch the attributes. And your output is going to be your vector query. So it's actually pretty straightforward to create a new vector query operator. And this is almost all the code. There's a little bit of stuff that I removed just so I could fit it on the screen, but this is like almost all the code. And So really, it's super easy to plug new operators into Solr. So then we put that into a jar. We copy that jar into some directory. So in this case, I put it in the lib directory inside of my library. So I have my SACO.NET Core. I have a lib directory inside of that. I copied in my Accenture Lucene operators into that. And so then you have to add it into the XML parser query operator in the Solr config. So this is our query processor, our XML parser, and I just call out the class, right? This is standard, Solr config structure. And this is the key. So whenever the XML parser sees vector query, it's going to call this class to parse it. I mean, easy, right? It really is. It's really not that hard. So now let's prove it. We're going to go to the query here. And what do I have to do? I have to do df type is equal to XML parser. I have to copy in the actual XML query into the Q field, right? So my query, it's an XML query. The query is this XML structure. And I want the title, the vector, and the score to come out. And so let's see if it works. It does not work. Oh, sorry, thank you. It is def type. There we go. Excellent. This is why we have experts in the classroom. And, I guess I can zoom this in a little bit. There we are, actually 1.001. So the round off error is a little more significant than I realized. But these are, the actual results. And so this number is, in fact, the Tanimoto similarity score. And if you went through and took those two vectors, and mashed those up to each other, you would see that you would get a true similarity vector score and a true similarity vector comparison operator inside of Solr. So now you can create your vectors, store them in the index, have a query vector, outcomes, true similarity scores across massive document sets. It's a thing of beauty. It really is. Okay, the code may not be a thing of beauty, but I'm sure yours will be. All right, so we're pretty much done. Just some final thoughts. I say this almost every year. It is time to break the tyranny of TF-IDF and BM25. I mean, for crying out loud, they are 40 years old. Have we not learned anything in 40 years? Yes, we have. Okay, there is a whole raft of machine learning, logistic regression. These things were invented before neural networks. These things were invented before the logistic regression was invented. And I know because I did regression analysis and I wish I had. Stop it. Okay, it's easier than you think. It really is. And it opens up a brave new world. Now, I have an actual paper that I've written on a whole suite of new operators called rational and comparable search engine operators with the goal of producing 0 to 1 scores that actually can be compared from field to field, from index to index, and from query to query, which opens up whole new worlds of possibilities. Like I can tell if I have any good documents, right? I can see if a document from this index and a document from this index, which ones are better or worse. And it's got a better proximity scoring and a bunch of other stuff. So kind of once you figure that out. So come to the Accenture booth. This is my, sneaky way of getting you all to the booth. Come to the booth, and I'll hand you a copy of the paper. All right? It's 20 pages. It's very dense. I apologize for that. Thank you. Any questions? I'll start with the.
In Lucene 7 something, there's a new, your technique of putting the weight into the position was clever, but it would be even better to put it into the frequency instead, to abuse the frequency and put whatever instrument you want there. And that's possible as of version 7 something. And there's already a token filter you can use that would completely cut out, that would not only be faster, but also completely cut out a bunch of the early stuff because you would use the stock, the limited term frequency token filter. And then you need to change your query to read the frequency as an integer and then divide by 100.
That's fantastic. We'll do that next time. That's great. You don't need any positions at all.
Right.
Fantastic. That's way better, way faster.
And then you don't need to use span.
I'll leave that as an exercise for the students. You're next.
You should call your talk next year the tyranny one to be a full house of people.
Okay.
That should be the title of your talk next year.
I'll keep that in mind. See if that passes the marketing department.
So, as you wait to the positions, aren't you missing a phrase matching and space matching?
Hey, remember, this is a vector input and a vector output, so it's not a full text square anymore, right? So exactly, we don't care. As far as we're concerned, tax space analyst is one term, and there's no tokenization on that at all. It's just it's like a string match, really, on the individual terms. But that did cause me a problem because I had one acronym, which was all caps, and so I had to stick a lowercase in there someplace. Oh, yes? No, not. Let me take that back. We are using this in a customer over 30 million resumes in a Solr cluster, and the performance is good. I don't know if I could give you a performance number on this particular operator. It's being used for, like more like this, right? This is a kind of like a more like this, only it's much more accurate. And again, if you don't trust what more like this is doing under the covers, you can code all the weights yourself. And so this is really a more like this mechanism. And so it's not used that like on a percentage of the queries in the whole system, but we've never had a problem with the performance over 30 million resumes in that particular customer. Although it could be more of a factor that's only used for 5% of the queries, for example.
I was curious, is there a source code shared somewhere so you can want to play with it?
No, but the presentation will be available, and that's most of what you need. And I would be, if I gave you the source code, it would be taking away the fun that you would have of discovering this yourself. And remember, I wanted more people to write their own operators. So, but we are working on this sort of operator package, so you could come to our booth, get a copy of the paper. We could create this operator package, sell that to you. Yes.
I was trying to implement more like this, but it is not giving good results from the one with Solr.
Right.
So I can change just the similarity part of the Solr query to get better results, or
I mean, you need to compute the weights yourself and stick the vector into a vector field, and then you need to do that, probably that same algorithm to compute the vector for the query. And then once you've done that, then this operator will give you the results as a regular similarity score. So it actually shifts a lot of the hard work to you, but it also opens up the power, right? Power to the people to incorporate any algorithm that you want, and also to incorporate external data, like maybe you have indicators from the outside that help you create better vectors. All right, thank you so much, everybody.